that don't know anything about the block, welcome to block 7. This is a really super tough block. It's considered the tough block. Welcome to the class, Cooper. And I cannot emphasize enough, if you need SIA, all right, you're on your phone, okay, good. Ladies and gentlemen, if we can, my suggestion would be to go ahead and be online about 5 minutes before the class starts. As you can see, now we're at 9:08, and I try to keep things jovial and on time because I know that your time is precious just as much as my time is precious. So let's see if we can't stay on time. And if you are having any issues, whether it's, technical or you need to go to the bathroom, let somebody know. I do not have a problem because, this is an important block, and if you miss a piece of information, it might be able to explain it to you to where you understand it and be able to succeed on the test, and you're gone and I don't know it, that's an issue. Now, I do record these sessions, and I try to give you that link within the day of these sessions. So that way you can go back and review. So that's the reason why I need to know that, okay, if you go to the bathroom, maybe it's in a section that I can go, okay, you can review it. It's not a big deal. But there are places where if you don't catch all the information, you're probably on that review. If you decide to review it, it may be an issue. And I see that happening a lot. So again, please try to be here a little bit early so I can, 1, check the mic, and number 2, to see who's missing right before we get ready to get started. So this particular block consists of a lot of information, and it overwhelms the students. Now, if you're good at keeping things organized and reviewing on a consistent basis, you'll do well in this particular block. If you like to ask questions, you'll even do better on this block. If there is anything that is confusing to you, and you don't want to ask me in front of anybody, I'm on Discord a lot more than a lot of other people, mainly because, I don't know, I just like the computer and playing World of Tanks. So I'm on well after, the 6 o'clock time frame. As, I get off probably between the 8 and 9 o'clock. And I'm on the weekends and down Fridays. So, please type in the question, ask me. Maybe, you might need some verbal assistance, and I can probably pull something up that is out of the norm that I don't normally do in front of the class that'll help you out. So my whole goal is to get you to pass this block. So, but it's up to you to ask the questions so I can help you out. All right. Without further ado, let's get right into it. We got 1 alpha, identify basic facts about timing and synchronization standards. Remember, there has to be at least a 70% in order to go on to block 8. Or is it called 8 now? Or is this 8? Did you guys have basic electronics?
Yes, sir.
Okay.
You had the 7 week or the 5 weeks in Nolan.
Okay. So you had the 5 weeks, and this is the 7. So they're classifying you guys as still as block 7. Okay. I was under the impression, because when I look at my handy dandy, breakout sheet, they've got you as the block 6 is now block 7. So it's kind of crazy. Anyway, we'll figure it out. But this is a very tough block. There are 40 questions on this test. 40. That means you got to get 28 correct in order to pass. Prefer that you get at least 30 or more. So there's your goal. Get at least 30 of these, so that way you don't have to worry about, just getting by. As always, we always come up with an FSC application, and it says that you guys are going to touch multi-channel systems. Well, if you've done anything with SATCOM, you're going to be touching it big time. If you're not in SATCOM at your next base, you probably have the chance to see it sometime during your career, depending on how long you want to continue. We're going to look at purpose of timing, timing standards, timing sources, time coordination, and distribution agencies, as well as timing jitter and network synchronization. So, how does this information pertain to you? So let me ask you, Airman Liverpool, do you game? Do you play games online?
Yes, sir.
What do you play?
Call of Duty.
Okay. How about you? Let me see if I can get this right. Basinski?
Yes, sir.
What do you play?
In fact, I also play World of Tanks and For Honor.
Okay. You're my new friend now. O'Brien, do you play?
I don't play many games online, a lot of offline stuff, but I play stuff online occasionally.
Okay. First-person shooter, strategy, what?
A lot more strategy, like RPG kind of stuff.
Okay. Rada?
I also play more single-player games offline, like I'm going through The Witcher right now.
Okay. So you know the law of surprise, which I like to call out on occasion. Okay.
Yes, sir.
Good. Right? Do you play? You can type it in. Oh, okay. I play COD and Minecraft. Oh, my grandson likes to play Minecraft. I haven't figured it out yet. Cooper, what do you play? If you play. And Last of Us, is that a game or interesting? Call of Duty? Okay, all right. I've never heard of it. That's a new one on me. Most of them that I go through, I am familiar with it. That's a new one on me. Is that something that just came out, or it's been around for a while, or it's a zombie survival? Wow, that's a good one. That's a good one. All right. So, Daily, do you play? And if so, what do you play?
Yes, sir. I also play mostly single player. I'm also working through The Last of Us right now.
Okay. And Ward? You can type it in. I'll have to check that game out. Not much a video gamer. Tabletop games and some mobile. Okay, that works. And Sergeant Rosales, what about you?
Yes, sir. I do play video games. I mostly play on PC, but I do have all the consoles, and I don't have a favorite type of genre, but I do like playing a lot of FPS and fighting games.
Okay. Now, this is all leading up to what we're about to learn here. And one of the things that I like to tell you about is when you're playing online against other people, that's where you start seeing some issues with what we're going to be discussing in the next couple days. What are those issues? Well, you ever heard of a ping rate?
Yeah, sir.
So that ping rate determines whether or not you have good connectivity and good reaction whenever you press a key. There is nothing I hate worse than being on a map, playing my tanks, and I got to make a right-hand turn, because if I don't make a right-hand turn, I'm going to end up in the river, and all of a sudden my ping rate just goes through the roof, and then it settles back down, and I've drowned in that river.
That's the worst.
Yeah, that is the worst. It's normally on, oh geez, what is that map? What is that map? Not Mines. Good grief. Abbey. There we go. That was called the Abbey. Of course, they just now came out with a couple more maps. One of them is Berlin. I have yet to play on it, and it just looks pretty rough. Well, anyway, everything that I just talked about in the ping rate when you're playing other people has everything to do with what we're about to witness here and go over. So with the purpose of timing, we look at what is it? Well, first of all, we got to sync up all of our systems where everybody is on time. That way, people can talk to each other and not have to worry about that lag or you're trying to understand them. It's all gibberish. So when we look at a system, and what you see here is it's an older system, but we've used this in the schoolhouse. You can see that at the middle of this particular slide, there's something called a multiplexer. You're going to be coming across it a lot. In fact, you guys probably don't realize it, but most everything that you see in this block, you are familiar with. We just use it in different terms. With a multiplexer, what you're trying to do is you've got a bunch of channels that have, might be one user on it. It might be multiple users on it. And I give you the fact with multiple users, you got a NIPRNet here, a local switchboard, a SIPRNet going into this multiplexer. So those are some multiple users going in on one channel. And then of course you have in the right-hand side of that multiplexer, you can see down at the bottom, you got computers and phones. All of those can be individual users and one channel each. And then it goes and makes an aggregate, which is a single entity coming out of the multiplexer, gets encrypted, goes to the satellite antenna, and well, there's more to it, gets modulated and sent up to the satellite bird in the air, and then gets relayed back down to the distant end so they can talk to each other or distribute it as needed. That's the system. You'll probably see this in block 9 when you get to the TSC 1, I think it's the 179. So we look at timing standards, and there's 4 that we look at: apparent, mean, atomic, and coordinated. And each one of them has a purpose. So we look at our history, and we look at solar time, not to be confused with hammer time. Dun 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 dun. No, bad. Okay, never mind. Apparent solar time is the least accurate. I take it you guys don't have a punny bone? No?
I am laughing a little bit. It's just I have to push to talk.
Come on, I try to keep it jovial, Anyway, the solar time is the least accurate, and the biggest thing is back in the day when they were using sundials to keep time. So everybody knows that with the sundial at high noon one day, it's going to be different at another day. So you have a lot of factors in here, i.e. the sun. Sometimes the sun doesn't come out, so there's no shadow on there. And of course, with the rotation, the orbit, which is an elliptical orbit, you got the tilt, which is the solstice. You got summer, winter solstice. You also have fall and spring. All of those are referenced with the tilt of the Earth, and you have wobbles in everything. Wobbles in the orbit and wobbles in the tilt. It is the least accurate time, and of course, when we upgrade to the mean solar time, this is when we started having like pocket watches and big town places where they had a big, huge clock in the middle of the town. So everybody is on time by relating it to the clock in town. Now, where did everything start? Well, back in the day, England, you had France, you had the Dutch, the Portuguese, the Spanish, all those did a lot of sailing around the world. And they developed these little tricks of the trade in being able to figure out where they were in the world. And it came back and started going, well, gee, maybe if we can do this mechanically, i.e. the pocket watches, i.e. the Big Ben of our days. And the reason why Big Ben came about was in London, that's how they were able to tell time and keep the time within the city, is when Big Ben went off. That was everybody's reference to, hey, my pocket watch is like a minute off, so I need to maybe speed it up or slow it down. They came up with this place called Greenwich, England. It is at the 0 meridian, and that's the latitude up and down on the world. And they reference this as universal time or Greenwich Mean Time. Fast forwarded to now, and we have something called atomic time. So we're improving with technology. It is the more accurate clocks. So now they have something called the International Atomic Time, TI or TAI. You're going, wait a minute, the acronym is wrong. No, it's actually French. So they use their words differently in what we look at it, but it is International Atomic Time. GMT is still considered our world's time standard. Universal time, same thing. You're going to see a lot of different interchangeable words in referencing that zero line and what the start of time is. We look at UTC time. Here's another word for that same place. This came back in 1972 is when they said, you know what, we're just going to keep this zero line. We're going to put everything in Paris, France as the keeper of time, but the zero line is now called UTC, but we still call it Universal Time or Greenwich Mean Time or, along those lines. The only problem is of course, the military's got to have one of our own times, which is called Zulu. So when we do missions, we always reference the UTC, Greenwich Mean Time, and all that other stuff that I just told you about to Zulu time. You might see two clocks in where you see missions. One will be local time, the other one will be Zulu time. Any time that we are referencing missions, it will be referenced to Zulu time. There are 24 official time zones, mainly because of the latitude. And I want to show you this www.timeanddate.com. I highly encourage you to go look this and check it out. It is not only the official time zones that you can look at, but also it has a plethora of other things that is on that website. So here is the time zone map that I pulled off of there, and you can see the many different areas on the map. You know what? Can everybody have a hard time seeing that like I am?
Yes, sir, it's a little far out.
All right, how about this? Better?
Oh,
Yes, sir.
see it.
All right, I'll do my best. I'll come back and blow it up even more and cut it and paste it and that. But this is on that timeanddate.com. You'll notice each of the time zones and the colors at the bottom and that. The things that I want to point out is let's look at the United States to start with. You can see that we have Eastern Time, we have Central Time, Mountain Time, Pacific Time, Alaskan Time, and I think in there should be Hawaiian Time. And that's to reference all the states. And everybody's kind of aware of that. But you notice that Alaska covers 2 time zones in theirs. But let's go point out something really weird. Let's look at China. China covers approximately 5 different time zones, but they only use one. They only use one. So with that in mind, each country dictates what they want to do, even though they have official time zones in there. So you look at Australia or India, they have diagonal lines. Believe it or not, they actually do those half hours. Now, that's not to say that here in the United States we don't have differences. I think Louisville, Kentucky goes with Central Time. I think the state of Arizona doesn't even observe daylight savings time. It's just their time and that's it. So it's just kind of weird how, you want the state or the country to, make things out. i.e., we're here in Central Time. Let's go to the next slide. When I can get through this, how about this? Change this. There we go. Let's look at timing source.
Hey, sir.
Yes.
I have a question. So when it says that atomic time replaced when TAI and UTC replaced GMT, where it says it replaces it.
Right.
By replace it, GMT is still in place. It's just called something different. Is that what it's saying, or is it actually?
No, it's actually we still refer it to Greenwich Mean Time or GMT or UTC or.
So they're all the same.
They're all the
same thing.
It references the zero line. It's what whoever it is. For example, if you're in London, England, they'll tell you it's GMT. You might be in Paris, France. They'll say UT. If you get us in the military, we'll say it's Zulu. So there's different names. That's what it's all going to, but it's still the same thing. It's a zero meridian is where time is referenced to. So as long as we understand that zero line or the prime meridian there, that's that latitude line, that's where the time starts. So whatever you call it, it still gets reference to that. That's all.
Okay. So it's not like okay, I got you.
Yeah, it's potato, tomato, tomato, that type thing. So it's just confusing, but it's not. It just depends on where you at and what they're going to use. Let's take a look at timing sources. And the reason I explain the logic behind Big Ben was the fact that the Big Ben was the time everybody referenced their pocket watches to. So when the clock went off, everybody would take a look at their watch to verify that their watch was either fast or slow or on time. So that's the reason why Big Ben in that case would be the primary and your pocket watch would be your secondary time. So for example, if I looked at my time here on the computer, it says 9:30 a.m. and I told you to go take a break. We're going to be back at 9:35. You take a look at your watch and say, well, I have 9:31. He's off time. Well, it doesn't matter because I just gave you the reference in how we're going to work things. So it's going to be 9:35 when you come back. And if you're here at 9:35 to your clock, you'll be early. That's a good thing in a way. But if you're like 9:33 and it's 9:35 on mine, I have the primary, you have the secondary. You're supposed to do the adjustment. It's just like with cell phones and things of that nature. Cell phones reference their time off of GMT. Where's that come from? Well, it comes from our GPS satellites and so forth and so on. So where is the logic behind it? The idea behind primary versus secondary is you always want to try to do the primary source with the most accurate. That's the key, the most accurate. There are two different types of oscillators that we look at used for our timing sources. We have the quartz and we have atomic oscillators. Now with the quartz, it is the least accurate of the two. It uses something called the piezoelectric effect. Do you guys know what the piezoelectric effect is? And if so, who? Can you explain it?
Is it when you generate electric charge across a crystal, or mechanical compression?
Okay. And it creates a vibration, and those vibration equals frequency, and we take that frequency and we reference everything to it. Yes, that is correct. Now there's two problems with it though. One is temperature, the other one is aging. Aging you can't control. Temperature you can. So therefore temperature is the thing that we can adjust, but as the watch gets older, so forth and so on, you might have to replace the crystal, replace the battery that goes to it. So those are some issues with the quartz oscillators. Back in the day when I was growing up, a $5 digital watch, use it for a year or two, then throw it away. Why? They were like $5 to $10. No biggie. Next up, we have something called atomic oscillators. So we've gone from the quartz, the least accurate, to the most accurate with atomic oscillators. Why? Because they are extremely stable. The two that we have are quartz and rubidium. All right, Aaron Ward is writing. What he has to say. Having internet issues. Okay, bouncing between comp and motor until I can figure it out. Okay. All right, we're good. Okay, with the two that we have, rubidium and cesium. Thank you for the heads up, by the way, Aaron Ward. The rubidium I've worked with in the old 206 palette. Rubidium oscillators are also in the GPS satellites and on the ground stations. But they're slowly but surely replacing them with the cesium, which is a much more accurate atomic oscillator. So these next two slides just give you an idea of how accurate the rubidium is versus the cesium. Now this one says very stable, drifts 1 microsecond in 24 hours. Look at the cesium. Look at it, 200 nanoseconds. That is very accurate when you compare it to the rubidium. We're going to look at time coordination. So we're going to use these timing sources and timing standards in being able to distribute timing to the appropriate agencies so everybody can figure out where to go and who to get. So they figured out with these agencies in Paris, France. That's how we ended up with 1972 and being able to figure out time on a whole when they started replacing it with atomic oscillators. They figured out it's like 86,400 seconds in a day. Now, with that in mind, they're going to use that to keep the accuracy. So what is a event? It is that time frame within that 1 second. Now we're going to show you some distribution agencies and how they use time to distribute. Now the biggest one, well, here's the distribution agencies: BIPM, USNO, and NIST. And again, let's look at BIPM. It says International Bureau of Weights and Measurements. Well, that doesn't spell BIPM. Again, it's French. It's Bureau International Precision Measurements. At least that's what I can think of as far as looking at the name. We have USNO, and then we have NIST. BIPM is the keeper of the time, but they also do other things on top of it, such as they are the keeper of what is a mile, what is a kilometer, what is milligrams, weights and measures, things like that. Now, why is that? Well, scientists need to have their equipment calibrated, so they take it to this agency, have them calibrate it, and then send it back. That is the reason why. So if you're trying to figure out what a pound is and you want to be extremely accurate, you're going to make sure that your machine is good, you got to send it to them and send it back. They'll send it back to you. Kind of. I mean, there is another process to it, but it's mainly for scientific equipment. The whole idea with this is it is a primary standard for the world, and they have something called leap seconds. Now, these leap seconds, today is the day where they will determine if we are going to add a second, or if we're going to take away a second, or nothing's going to change. So the 30th of June is one time that they look at changing the time, and also the 31st of December. So there's the two time frames where they manipulate the time to either adjust accordingly. How they're able to figure that out, I don't know. So this is what the website looks like. Bureau International des Poids et Measures. Top left-hand side. That's what it says. I just brought the web page up. I'm not sure if you can see it, because I can barely see it myself, and I've got a pretty big monitor. But you can go back and go www.bipm.org and get to the website. There's the English version. Make sure that you have your, the captions where it can translate French to English, and it'll work. So next up, we have something called the USNO. Well, the USNO is the DoD agency. Now, its headquarters out of Maryland. However, where they keep all the time is right down the road from us. It's in Pensacola, Florida, better known as the Blue Angels, where they're at. They are the keeper of the time for us, the DoD. Now, you'll notice down here on this slide, it has a phone number. 202-762-1401. When you dial it up, give it a second or two. Most of the time you can get through on the first couple rings. There's been a couple times where I can't get through unless you dial it 2 or 3 times. Now, what you're going to hear is you're going to hear some time hacks. Every 10 seconds, they're going to give you UTC time from Paris, France, and they're going to give you Eastern time. So it's UTC for Zulu, and then you're going to get local there at Pensacola. Again, you can look it up on the website. Here's their website, United States Naval Observatory. Notice it's in Washington, Northwest Washington, D.C. I'd still say it's right on the edge of Maryland. But you can look through this website. They do have history to it, and from what I understand, just recently they're going to replace all of their atomic clocks with more improved atomic clocks. I just recently seen they're going from a rack system to more like a very small cabinet, and like a 2-file drawer cabinets. That's how the sizes of these atomic oscillators have got and how accurate they are now. It has everything to do with technology and the improvement. Next up, we have something called NIST. Now, before I go any further with NIST, did you guys go out and block forward? Did you use the radios for anything when you hooked them up to the antennas?
Like are you saying, like, did we, like, broadcast anything, or, like, send out anything?
Yeah, did you talk to each other on the antennas?
Yes, sir.
Okay. Did you have anything to do with time hacks? In other words, listening?
Like clicking? It was clicking?
Yeah, you go dee, 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 and then over a period of time, I think it's every 30 seconds, it would click in and say the time is, and it would give you the universal time.
Oh, no, I don't think we ever did that, sir.
Okay. Well, anyway, the reason I ask that is sometimes you get instructors that, can see that if the class is really good, they'll bring the radios out, and when they hook them up to the antennas, they'll try to listen to NIST. NIST is over-the-air broadcasting. It's 2.5, 5, 10, 15, and 20 megahertz. Now, why is that important? Well, if you're having problems trying to reach somebody on HF, and you want to know that your system is working, by going to one of those frequencies, you eliminate that. Well, I know the receive is working fine. So when you pick it up, then it's not an issue. Now, you'll see that on this slide, it'll say WWV, WWVH, WWVB. WWV are the call signs. V is the headquarters out of Maryland. VH is Hawaii. VB is Boulder, Colorado. There is one other frequency that is out there called the 60 kHz. Goes a pretty far distance. Again, it's at Boulder, Colorado. It is not at Hawaii. Can you hear Hawaii here at Keesler Air Force Base? Yes, you can. I have heard it a couple times. Once real early in the morning, about, I want to say about 6:30, and once about 1 o'clock in the afternoon. It was one of the most strangest things I have heard. It was, and how can you tell which one's Hawaii and which one's Boulder, Colorado? Well, there's a history lesson behind it. Boulder, Colorado is the male voice. Hawaii voice is female. That's how you can tell. And when you listen to them, the Hawaii voice came in first and then followed up with the male voice afterwards. One of the strangest things I've ever heard, but it works. Can you get it all the time? No. Is it a rarity? No. It's just one of those things that the conditions were right with HF, and everybody knows that the conditions have to be right for HF in order to hear it. Again, you can dial this number up, 303-499-7111. It's only going to give you the universal time, UTC. You can also go to the NIST.gov website. Here's the website. Looks kind of crazy, but they actually have a couple videos in there, which I thought was pretty interesting. But if you go through and toggle through all the publications and stuff like that, you'll see one on the history on the Boulder, Colorado, why it was there, i.e. World War II. And what happened to Hawaii? They've had to relocate a couple times because where they put the first antennas, the ocean decided to come and talk to them a little bit earlier than normal. In other words, erosion took out where they were at. So they actually had to go more inland and put it up on top of a mountaintop. Kind of interesting. So those are some things that you can go look at later on down the line. Timing jitter, changing gears now. Remember I talked about the ping rate? Here we go. We're starting to see that undesired shift of data or clock. In other words, when the line is getting noise on it, or there is something from a server that might have an issue, might have went out, glitch in the power, things like that. You just don't know what actually happened. Those signals are going to get a lag to them. And just like with anything else, with digital signals, the further you're out, the more lag you're going to have. In other words, distance. So if you're 500 feet versus a mile, well, the one with the mile is going to have a serious lag issue. But with timing jitter, the big thing is we look at it causes problems for us when we're trying to sync things up. We have short-term jitter and long-term jitter. The short-term jitter is easiest to explain. Everybody goes on YouTube. At least I don't know of anybody who hasn't been on a YouTube. So when you go to a YouTube website and you're having some short-term timing jitter, what you're going to see is that nice little circle come into play, the blank screen, and that circle. And then you're going to notice down at the bottom, the bar is starting to come up as it gets more and more information. Once it gets enough information to justify playing the video so it can sync up audio with the video, then it will play. Now there are some times that where the buffer has a problem with the timing jitter, The buffer is what we call elastic store. Now, with this elastic store, it stores that information up and it decides, okay, I think I have enough information, so when I get more and more information, I can play this at a steady rate. So that's what short-term jitter is. It's basically a bunch of information coming in and being stored long enough to gather enough information to play the video at a constant, smooth rate without having to stop and wait for more information to come around. Back in the day when we had 56K, that was always a problem because you would see the videos start, and maybe the audio would be lagging behind, and it was really bad. But nowadays, with Elastic Store, with the buffer and that, it's eliminated most of the problems. You still get it every now and then, but it's there. All right, Sergeant Rosales is writing here. We also have something called long-term jitter. This is where everything is on time, but because of the distance between each other, there's going to be lag. All right, so he's got to go to the bathroom, so here's what I'm going to do. 9:48, let's take 5 minutes, go to the bathroom, come back. Let's be back at 9:50, make it even, 9:55, all right? So being paused. If everybody is back. Liverpool, you back?
Yes, sir.
Brzezinski?
Here, sir.
Okay. O'Brien?
Here, sir.
Okay. Rada?
Here, sir.
Wright is writing. Get it? Wright is writing. And Cooper, you here? You can write it in chat. Daly?
Here, sir.
Okay, and I got Ward and Rosales. So who's missing? Cooper? Okay, good. Good deal. All right, let's continue on. We left off with long-term jitter. Now, the way long-term jitter, like I told you before, even though there's highly synchronized clocks, but the problem is when they talk to each other, they're unsynchronized. And the only way that you can get these things to talk is something called phase lock loop. So what it's going to do is it's going to take the line clock, which is coming in, and it's going to take the internal clock, and it's going to compare the two, and it's going to make its own time to where everything syncs up. Get it? Syncs up. Bye. No? Okay. Boy. No pun meisters out there? Wow. All right, we have somebody, tough crowd, that is true. Okay, synchronization. There are 4 different types of network synchronization. The first word, as long as you say the dinosaur, I know what you're talking about. Isochronous is the way I say it. There may be a different way of saying it. Then there's mutual, master clock, and master slave. So let's take a look at each one of these. So Isochronous is basically you have 2 nodes. You're not going very far with this one. The idea behind it is even though you may have some, synchronized clocks within your internal system, they're going to average it out and use elastic store in order to make things happen. So with mutual, it's a little bit different. They have nodes everywhere, and again, they're going to average everything out to give them a synchronization within those particular nodes, so to speak. With the advent, if one of these nodes fail, they just go back to re-averaging everything, and oh well. I like to equate this to the LAN parties that they have up there in the dorms there. when you're playing against each other using multiple computers, and then someone says, well, I've had enough, I'm going to bed or whatever, and then they take their computer, that's basically what happens, is everybody syncs their time back up once that has been removed. Then we have master clock. This is an example of the Big Ben that I've been talking about in London. If that master clock goes, everything goes. Now, if you were to research Big Ben right now, you'll find out that it is in rehabilitation. In other words, they are taking it down, putting in new mechanics, upgrading everything to where it still has the original chimes, but the information, from what I understand, is they're still going to have mechanicals, but it's going to be much more precision monitored. And if you ever get online and decide that you want to research a little bit about Big Ben, go to the History Channel section on Big Ben, and you'll see how they were able to keep Big Ben on time with UTC. And it's really weird. They would use the old halfpence, which is a half penny in our language, and they would put on the pendulum to get it back in time, or they would take it off in order to bring it back in time, just depending on how everything was working. Most of the information I saw on it, it's probably within 20 seconds of UTC. For the couple times that they showed you, when it was on time, and then they showed you whether or not that they took a halfpence off or put a halfpence on or just left it. It was pretty interesting. And then we have something called master slave. Now this one is what we call the defense agency using this one. Why? Because if you think about it, this particular style of master slave is like the pyramid scheme. If you have the top clock and you got 2 underneath of it, or 3 or 4 underneath of it, and it branches out even further. If the master clock goes, someone is going to take over and take its place, and it will be the master clock, and so forth and so on. The idea behind it is the reason why we use it this way is because that if we get into a wartime situation where they start taking out bases, then those bases are going to alternate with the timing sequence as to who gets what where. So we've covered primary purpose of timing standards, timing sources, time coordination, distribution agencies, timing jitter, and network synchronization. A lot of information, isn't it?
Yes, sir.
Any questions? All right. Again, this will be recorded for your pleasure, and again, I'll put it on YouTube and give you guys a link for it if you want to go back over it. We have a long weekend, so this will be a wonderful time to look through that. The next one we have is what I call the fun one. This particular style is dealing with signal formats and what we call analog to digital. So we're going to identify the relationship of basic facts, state general principles associated with the principles, capabilities, limitations of multiplexing. Remember, you got to get 70%. That means you got to answer 28 out of 40 correctly to go on to the next one. Again, you're going to be dealing with multiplexers. Probably touched them and didn't realize that you touched them. We have general multiplexing terms, input data relationships, types of multiplexing, modes of TDM, demultiplexing, signaling formats, and analog to digital conversion. Let's get right to it. So here are the terms. We have analog digital. Everybody pretty much knows the difference between those two. I like to associate 3 words with one of them. That way I know what the other one is. It's normally the opposite. So I'm going to pick analog because it's fun. And you'll notice that first line, it says an infinite number of values. Well, okay. It's also unlimited. And another word which is pulled straight out of some of your electronic textbooks, they'll say indiscrete. Okay. Infinite, unlimited, indiscrete. So let's take a look at digital. Well, it's the opposite of analog. So it's going to be limited, finite, discrete. In other words, you know what digital it has. It's very limited to it, whether it's plus 5 volts or 0 volts or it's plus 10 volts, all the way down to negative 10. I mean, just depends on what it is. There is a cutoff with it. Very limited. So next up, you guys have seen the word bit before, ones and zeros. Multiplexing, this is where you combine 2 or more users. And again, channels is more of a better word than users, but users are normally interchanged with channels. But let me add this to it. When you say users, there could be multiple users on one channel. There can't be multiple channels for one user. So that's where the issues is. When you look at multiplexers, they always come in channels. And depending on if you have one user, you can interchange channel/user. But when you add users, if you have a 24-channel system, you don't want to say I have 24 users and it's all on one channel. So there's your little thing with that. So make sure you get the terminology correct. Combining 2 or more channels into a composite signal or aggregate. In other words, you've got multiple people coming into the multiplexer, but when it comes out, there's only going to be one stream of information. And it's going to normally work off of what's called TDM, time division multiplexing. So this is what one looks like using that particular term. When you have multiple channels, which are user inputs, and you put it into a string. So you can see channel 1, channel 2, channel 3. Channel 1 is the diagonal lines, channel 2 is the solid bars, and then you have the horizontal bars. So you can see that we have the first stream coming out, shows that you got channel 1 in the front, channel 2 is next, and channel 3 is last. And then it starts repeating it. That's the TDM here. You're using time to break everything up, so when you send that information, it's all one data stream. There's not multiple things on it, but it's just a sequence of events happening. We look at sampling. This is not to be considered like going to the buffet at the casinos when they finally do open up. Highly recommend them, especially the beau rivage and the breakfast. But it doesn't look like you guys are going to be able to get there when they finally do open up. I think what they're talking now in September and starting to loosen back up because they went up the scale instead of down the scale and start loosening everything up. So sorry about that, guys. Sampling, this is where we're going to take the signal and we're going to sequentially divide it up in equal parts, and then we're going to use a line to get to the amplitude portion of that analog signal and develop a period or a sample of each parts of those lines in a sequential order. We have something called frames, and what frames are is it's a sample from each of the channel to determine where they're supposed to go in that frame. And the idea with using these frames is channel 1 goes in the channel 1 slot, and it's each one of those are sequential. So if you got 24 channels, it goes 1, 2, 3, 4 all the way up to 24. It doesn't get out of line. You can't put number 20 in front of number 9. It doesn't work that way. Everything would be out of sequence that way, and when it gets to the dissonant end, it's not going to know what to do when it finally gets to that part. You have something called non-information bits. The bottom sentence here, frame bit, start bit, stop bit, stuffing bit. All those play into it. It's also called overhead. And I'm not sure who your block instructor was, when they talk about all these non-information bits, if they ever referenced it to overhead. Please understand, there is the intelligence that you're sending down the line. That is the information bits, and then the non-information bits are things like, where does this have to go? Does this go to channel 1? Does it do this? This is the beginning of the word. This is the end of the word. So that's what's called overhead. So you got to add to the bandwidth when you factor these things in. Oh, speaking of bandwidth, here you go. You got two different styles here. You got, one can be the rate, one can be the size. You know, what are you in referencing it to? Because we deal with radios and we deal with multiplexing. So when you talk radio bandwidth, we're talking, okay, from 300 megahertz to 3 gigahertz. That's that international band. Or how fast does it go? 56K? You know, what is it? You know, is it 2 gig? So you can see that what is it referenced to figure out how that bandwidth is going to work out. We have a couple different types of input data relationships. This is the first one, which is called async. This uses, well, along that 8-bit word, you're going to have a start and stop bit to determine, okay, where's it got to go? Where does it got to end? Where does it start? This is the precursor of the computer. Synchronous is what I like to reference to as a train coming up to a depot. You've got passengers that need to be put in, passengers that need to be pulled out. Each one of them is assigned a boxcar. In our case, I'll just give you an idea. We got, let's say, 10 boxcars. With synchronous, everything is at a fixed rate. So you only have one place where only one boxcar can get off. So the idea is the train pulls up, you have, let's say, 10 seconds to get everybody off and 10 seconds to get everybody back on. If you don't meet that time, you don't get on. If you don't meet that time to get off, you got a problem. Normally getting off is quicker than getting on because there's an interchange between those two things. So you have the next boxcar come up, boxcar number 2. There's nobody getting on and nobody getting off, but it still uses the same amount of time to open those doors. Well, where is everybody? Oh, well, I'll wait, and then bam, close the doors. Here's boxcar number 3. It only has people that need to get on, but it still uses the same amount of time, you know, to get stuff off and then to put stuff back on. That's synchronous. The way that I can think of is when you're using security cameras, because it's always on and it always goes through each one of the cameras if you have it logged onto that way. So it just gives you an idea of what it could be used for. Isochronous is a mixture. Isochronous means there's going to be a ton of overhead. It is what I call bandwidth hog. I don't see a whole lot of more of uses out there in the Air Force for this. They're probably still around, but I haven't come across it. We used to use it, but because it was such a bandwidth hog, everybody started doing away with it. So what is isochronous? Well, it's asynchronous at a synchronous. Well, asynchronous means you got to have stop and start bits for everything, you know, so forth and so on. But if you don't have that boxcar full, you got to stuff it, and that's where a lot of the overhead comes into play. And they say a steady stream of video and voice to the distant end. You could look at that as cameras and what we call VIDs, visual intrusion detection systems, which rely on video cameras and sensors in sending that information back to, let's say, the WSA headquarters. WSA meaning weapons storage area. They use that a lot. And in most cases, it's probably about 2 to 3 fences, cameras about every let's say 20 to 50 feet, overlapping each other, looking on the outside, and plus you have sensors in the ground, sensors on the fence, and that's what the cops are for inside, is to go check those fences out when they have an alarm like that. Normally it's a bunny or something like that getting through. Been there, done that, don't want to go back. Next up, we have something called frequency division multiplexing. Now, the easiest way that I like to associate this with is the old style cell phones before they went to TDM. How did it work? Well, if you had a cell phone, there was basically, when you flipped it open, it was searching for a frequency that was open to use at the cell site. It would find one, lock it into place, so when you dialed, now you had control of that frequency. Here's the problems with it. With that frequency, if you travel from one cell site to another cell site, it's got to hand you off. Well, the problem was the handshake between those two most of the times did not work very well, and it would drop you. Why? Because maybe that frequency you just had is taken up and it's searching for another frequency and can't find it. The cell site might not be as large as what you just came from. In other words, let's say a 30-channel site versus a 10-channel site, where everybody's on the 10-channel site, so when you came from the 30 to the 10, it was full, it's going to drop you. And that's where a lot of the problems of the earlier cell phone systems had major problems with. Let's fast forward to today. Now we're using something called TDM. So this is a lot to do with how we assign everything to a information part. Okay? Information part being a time slot. So if you pulled open your phone now, the cell site automatically knows that, hey, you opened it up. Most cell phones have a frequency range between, I think it's 750 to 1.5 gig, but it's all on channels now. It's not just frequencies, it's channels. So now when you're assigned a time slot to talk on your phone, it makes it a whole heck of a lot easier to hand you off to go to the next site. Here is an example of what happens. You got frame 1, 2, 3, 4, 5, and again, if you're talking back and forth, you're going to be taking up one of those channels. We also look at something called modes of TDM. We got synchronous and asynchronous, and I go through this real quick. Synchronous, again, it's like that train coming up to the depot. You got X amount of time to get stuff on and off. If you don't use it, the bandwidth is wasted. You got an example here that you look at frame 1, everything's full. It gives you the frame bit. Here it is in sequence. You got frame 2, well, all of a sudden we don't have anything to put in Charlie because no one's using it. So that's wasted. You look at frame 3, well, now I've got Bravo and Charlie not being there, so it's wasted. And then the last frame, you got Bravo, Charlie, and Delta that's not there, so that bandwidth is wasted. And again, it's a constant synchronous rate. Doesn't matter if you have asynchronous or isochronous, it's still going to keep its time. Well, next up is async, and again, this is what the computer's using nowadays. This is going to assign time slots to active channels. The interesting thing is it's very efficient. Now, most of you that are in the dorms right now have access to Boingo. And believe you, I understand Boingo is not the best. But let's take a look at the issues with Boingo. Well, think about it. You got a dorm that's probably, 500 strong in there? And if everybody is using the computer, waiting for their time to get on Boingo, that's an issue, isn't it? But let's just say back in the normal days where everybody was in the classroom and not in the dorm, people that were on nights could get up, log on, and play an online game with no problems. Why? Because it's fast at that point. But when you start putting a lot of people online, then that bandwidth has been exceeded, and it's a problem trying to play a game or even just watch a Netflix video on there. And this is an example of async and how we can say, well, it can get faster when there's not enough, when there's, least amount of people on it. But you max this thing out, yeah, you're going to have to wait your time. Get it? Time? Modes of TDM, time division. Never mind. Anyway, look at frame 1. You have all the users using their channels. You go to frame 2, you have Charlie that's not using it. And look how quickly that you can get to frame 3. Well, Charlie's not there anymore, so it doesn't have to use that time slot. So it fast forwards to frame 3. Frame 3, you can see just Alpha and Delta using it, so it's even quicker to get to the next frame. So you can see how the async can be flexible when it's maxed out, but when everybody starts getting off, which will be that 1-2 o'clock time frame in the morning, you could probably play an online game with no problems. Async, again, is bulky. Not as bad as isochronous, but async is bulky when you've got to put a lot of users in there. The nice thing is when you don't have those users in there, then it starts to speed up quicker and quicker and quicker. You can see with frame 1, we have stop and start bits. We also have the framing bit to show where it is. Now there's more information or non-information that's fitted in there, but that's a can of worms we're not going to open up because this is basic information. When you get to frame 2, this is where Charlie is not there, but you notice it's going to be quicker. Quicker because now I don't have to use Charlie's time slot. Now, when you get into the point where you get into isochronous, this is where you have a lot of overhead, in other words, non-information bits. Frame 1 is identical to the frame 1 back into async. Frame 2 is the same setup, however, Charlie needs to be filled with non-information bits, i.e. stuffing bits. That's so they can keep it synchronous. In other words, just like that train station. The problem is now you're going to have to fill it up with something that doesn't matter, but in order to keep everything on time, you got to. And that's stuffing bits. That's where that non-information stuffing bits comes into play. Again, isochronous is the memory hog, or not memory hog, but the bandwidth hog. Now, demultiplexing. So we've talked about multiplexing, which is getting it into a single aggregate. What happens when it gets to the dissonant? Well, demultiplexing takes place. And this is where you've got to take that stream and divide it out, and that's where the framing bits come into play and say, oh, okay, this is number 1, this is number 2, this is number 3, and then start all over again. Number 1, number 2, number 3, like it is on this particular diagram. Here's where we start getting into signal formats. In other words, we're going to be sending that aggregate to the dissonant, or we're going to receive that aggregate, and it's going to be in a certain signal format. We have 3 types that we discuss. We look at non-return to 0, we look at return to 0, and CDI. So I'm going to try to keep this as simplistic as possible for you. Before we go anywhere onto those signaling formats, look at this number. How do you read it? Do you read it from left to right or right to left? Most of you will say left to right. A couple of you will say right to left. So who is correct in looking at this number called 1 million? Wouldn't that be nice if it was dollars? If anybody was paying attention. So since you answered me, how would you read it? Left to right, right to left? Masinski?
I would probably read it left to right.
Okay. Well, most people's going to say that. Why? Because when we read information and say a sentence, we're going to read it from left to right. Realistically, the number is read from right to left because we got to find the lowest denominator here and work our way up. Not trying to put you on the spot, but that's normal. But the problem that we have nowadays is we always like to use that left to right when realistically in electronics we should be going from right to left when doing numbers. And what does that equate to? Well, when you deal with 8-bit words, it works the same way. When you deal with data streams, it works the same way. We always take the lowest denominator and work our way through. So you can see that an 8-bit word going from 1 through 8, least significant digit all the way to the highest significant digit. Well, it goes 1, 2, 4, 8, 16, 32, 64, 128. That is an 8-bit word. How does it flow out of the stream? Well, you have clock cycles starting from right to left. That's how everything should work. If you take a look at an O-scope, it should track from right to left. Now, with the spectrum analyzer, I have noticed it always goes from right to left when it's looking at everything. But it also starts, which I noticed a while ago, that the higher frequencies are on the left and the lower frequencies are on the right. At times. When I say at times, when we're looking through specifics in how the aquadag is. Aquadag meaning that front panel that beam is flowing on. But take a look at it. See if your O-scope does that. See if the spectrum analyzer does that. When we look at the first format called NRZ, non-return to zero, that is the name of it. It's telling you the signaling format will never return to zero halfway through the clock cycle. And there's that clock cycle I was telling you about, bottom right-hand side. It works like in most instances you'll say, well, it's a backwards sine wave. Well, that's true, but O-scopes track from right to left when they're dealing with numbers. With non-return to zeros, the big key thing here is that first sentence. It is the most common format of data that travels within a multiplexer. Well, what does that mean? Well, you have all these channels with users. The users could have any signal format depending on the equipment that they have. They send it to the multiplexer using ones and zeros in that format. When it gets to the multiplexer, it changes it to NRZ. Then when it gets ready to send it out to the aggregate side of the house, most of the multiplexers that I have seen either change it into a CDI, which is another signal format that we're going to go through, and a NRZ. So those are really common that I have seen. I'm not saying that you can't send something different out. I'm just saying those are the most common. We're going to look at two different types. We've got neutral and polar. So neutral is from +5 to 0, +5 being the 1 and 0 being 0. You'll notice that last sentence down there. It is not self-clocking. What does it mean by not self-clocking? Well, it doesn't resemble the clock cycle in our stream. That's an internal clock. So what we have to do is not only do I have to send the data, but I also have to send a clock signal with it in order to tell the distant end, hey, this is the clock cycle that it's on. So it's added information that you've got to send. So NRZ in itself is not self-clocking. We're looking at neutral. So I'm showing you the signaling format when we look at data. Now, the way we do signaling formats is we have a clock cycle, we have the data itself that fits into each one of those clock cycles, we have the data which is going to determine what our signal should look like. So with the 0, it's always going to stay 0. With the 1, it's going to go up, and it's going to stay that way even halfway through the clock cycle. Something should happen, but it doesn't. That's the nature of NRZ. You have another data of 1, and then you have 3 zeros in a row. So it goes from the +5 down to the 0 for those 3 zeros, and then back up to a 1, back down to a 0, then back up to a 1, and then a 0. Nothing happens halfway through the clock cycle, so the dis-and-in does not know when it clocks. How does it stay in sync? That's the reason why we send a clock cycle along with it to tell the dis-and-in, hey, this is how it's synchronized. So let's look at polar. Now the difference between neutral and polar is pretty obvious. One has a 5-volt difference of potential. This one has a 10-volt difference of potential. Again, it's not self-clocking, but the polar has a big advantage over the neutral because of the distance. In other words, when you send it down the line, you only have a 5-volt difference. When you get down to the dis-and-in, it may only have a 3-volt difference, maybe even a 2-volt. Well, the dis-and-in may not be able to determine whether it's a 1 or a 0 from the signal format. That's the reason why when you send a 10-volt difference of potential, then you can determine, that 500-foot line that the neutral can't handle. Well, now the polar can. It'll be able to differentiate what is a 1 and what is a 0. Again, it's not self-clocking, so you have to send a clock cycle with it. Here is what we are seeing. You'll notice it is the same identical waveform from the neutral. Let's go back up to neutral. There's neutral. Here's polar. The only difference is there's 10 volts instead of 5 volts. Nothing happens halfway through the clock cycle, so there's no way to determine how to sync it up. So you need to send a clock cycle with it. Next up, we have return to 0. There are 4 different types. This one is the namesake, return to 0 halfway through the clock cycle. A little bit different than non-return to 0. We look at 4 different types: neutral, polar, bipolar, and bipolar with 0 suppression. When you get to the NSM today, because we're going to do that at 1 o'clock, you're going to see RZ bipolar, and you will see RZ bipolar with 0 suppression. You'll also see NRZ in the NSM 50. Let's take a look at neutral. Again, it's the same way as NRZ neutral, except for something happens halfway through the clock cycle. Wait a minute, it's still not self-clocking. Crap. Well, let's take a look. The difference is instead of neutral NRZ, where nothing happens halfway through the clock cycle, anytime that there's a data of 1, something actually happens halfway through the clock cycle. You can see we have a 0 starting from right to left. Nothing happens. The 1, okay, it goes up, but you notice halfway through the clock cycle it does something. The name returns to 0. Okay. Again, we have another 1. Halfway through the clock cycle, it returns back to 0. The namesake, return to 0. We have 3 zeros in a row, nothing happens. We get another data of 1. Something happens halfway through the clock cycle, we return back to 0. So you can see how return to 0 in its namesake and what actually happens. But again, this one is not self-clocking. We have RZ polar. Now the difference between this one is 1s are a +5 and 0s are a -5. Look at that. It is self-clocking. Self-clocking. Oh, gee, something happens every time halfway through the clock cycle. The name RZ, return to 0, happens every clock cycle. Let's take a look at the first one starting from right to left. We have 0. So we're going to go down to the -5 because that's where logic 0 is. Halfway through the clock cycle, we go back up to 0, return to 0. With a 1, we go up to a +5 because that's where the logic 1 is. And halfway through the clock cycle, we come back down to 0, return to 0. Same for the next one. Here we see a 0, and here's where the difference is between the 3 signaling formats we just looked at and why this one is self-clocking, because something happens halfway through the clock cycle. We return to 0, whether it's from a -5 or a +5. So the 3 zeros in a row halfway through the clock cycle is going to return back to 0. So it goes down to a -5 for the 0 logic and then back up to 0. So you can see that the reason why this one is self-clocking, it's pretty evident. So that's our first one for self-clocking. Then we look at RZ bipolar. Now, I want to caution you with this one. RZ bipolar also has another name. When you look at the NSM-50, it is called AMI, Alpha Mike India, better known as alternate mark inversion. Now, I'm going to point to the word bipolar or alternate mark inversion, and you're going to see why they named it those two. Again, this one's not self-clocking, but it also said something about zero suppression in making it self-clocking. So bipolar itself is not self-clocking. So let's take a look. You can see that the logic 1s are either going to be a +5 or -5, and 0 is going to be 0. Okay, let's take a look. The reason why they call it bipolar is whatever the first data is, it's going to flip on the next one. In our case, we start with a 0, it stays at 0. The first data of 1, we're going to go to the +5, and then halfway through the clock cycle, we're going to go back down to 0. Hence the name return to 0. The next data of 1, because we went to a +5, it's going to alternate and go to the -5 for its logic level 1. And it's going to constantly flip-flop every time it sees a data of 1 come in. So that's the reason why they call it bipolar or alternate mark inversion, because it flip-flops between the +5 and the -5 for all data 1s. Then we're going to look at RZ bipolar with zero suppression. Now this one, you have to tell the computer that the distant end what you're sending. If you don't tell it, hey, I got RZ bipolar with zero suppression, it's going to think it's RZ bipolar and it's going to be a problem. Why? Because RZ bipolar is self-clocking. So there's your second one. We have RZ polar as self-clocking, and now we got RZ bipolar with zero suppression as self-clocking. Well, why is it self-clocking? Well, anytime that you have a string of zeros and you tell the front end to tell the distant end, hey, this is how we're going to work this, it's going to throw a bit violation on one of those strings of zeros depending on the number it sends to the distant end. The bit violation being the emulation of what happened to the last data of 1. Let's take a look. So right to left, we have a 0. Nothing happens. First data of 1, we go to the positive side, because we always like to start with positive. The next data of 1, we go to the negative side. So there's your bipolar. There's your alternate mark inversion. Well, with this one, it's telling the distant end, hey, after a string of zeros, in this case 3 zeros, on the 4th 0, we're going to throw a bit violation. Okay, what the heck is a bit violation? Well, whatever the last data of 1 is, it will emulate it. And what do you mean by emulate? Well, it's going to look back down to the last data that was entered as a 1, and it's going to replicate it. Well, wait a minute, it should have been flipped if it's a data of 1. Yeah, that's true. That's called the bit violation. So whatever that last data of 1 is, it's going to duplicate it and say, hey, that's my bit violation. The dis-and-end is going to go, hey, I got a bit violation, so I'm going to sync my information back up to where it is clocked now. That's how they get the self-clocking out of it. The dis-and-end knows, hey, every 4 zeros in a row and I throw a bit violation, I know that I have to resync things, and that is being in time now. So you can see how this is supposed to work. Again, you'll see things like, and I'm going to give you a couple from the NSM. Bravo 8 Zulu Sierra. That's B8ZS, which is bipolar with zero suppression on, and they're looking at 8 zeros in a row, throwing a bit violation on the 9th zero. So that's how they're able to tell it to the dis-and-end. By the way, that's North American, and it's a T1 line. You guys have heard T1 lines, right? No? Maybe? Okay.
Maybe.
No? No, we're going to cover. Yeah, we should be covering hierarchy too in a little while. So another one is a B6ZS, which is Bravo 6 Zulu Sierra. That's a T2 line. A Bravo 3 Zulu Sierra is a T3 line. This one right here is a Bravo 3 Bravo 3 Zulu Sierra, which is a T3 line. It's throwing the bit violation at the 4th zero. Again, you can look this up on Google, and it is kind of crazy with that. Go ahead.
In the book, it shows for like B8ZS that the bit violation happens on the 8th one, not the 9th one.
That is correct. Nice way of pointing it out. And even though that it says B8ZS, if you take a look at Google, that would be incorrect. That is an incorrect statement on the study guide workbook. I've been trying to get him to change that. If you look it up on Google, it's really tough to decipher it. And when I showed him that, I mean, he's pretty acceptable. He'll change it, but we're kind of crammed with all the other stuff that we're doing a new course, so it's on the back burner. Now, you're fine. Don't worry about it. Let me explain why. We're just showing you signaling formats and how they're represented out there, but we get, on occasion, we'll make mistakes. Now, will you see that anywhere in the confines of a test? The answer is no. What we're more interested in is showing you what is clocked, self-clocked, and what isn't. And we're trying to explain it the best of our abilities for that. So that's the reason why you shouldn't, you don't have to worry about freaking out on that B8ZS on there. So he is aware of it. It'll change one of these days, unless the new course takes over. But you can look it up on Google, and the way they do it is, heck, I'm not even going to go there because that's open up another can of worms. But you are correct. The study guide workbook is incorrect, and you don't have to take it with a grain of salt. All you got to worry about is what is self-clocking and what isn't. There are two modes that we talked about, or two signaling formats we talked about. One is RZ polar, that's self-clocking, and RZ bipolar with zero suppression is self-clocking. We got a third one to do here in just a minute. Excuse me. Did that clear that up for you?
Yes, sir. Thank you.
Yeah, we're going to make mistakes. We all do. And it's just done, with research that I do and he does. Sometimes we get it right, sometimes we get it wrong. But it's not a question that we're going to ask you on the test. You just need to be aware of it. Because you're going to deal with this on the NSM. When I say you deal with it, all you do is you program it in. It does everything else for you. And then the last self-clocking mode, called conditioned diphase. This is a little bit different than all the signaling formats that we just went over, i.e. the, what is self-clocking using the +5 to the -5 to the 0 and so forth and so on. This one's a lot different. It uses something called, and I say one word, transitions. Why? It does not care about a +5. It does not care about a 0. It's more worried about what happens within a clock cycle than it is anything else. Yes, it still uses the 0 to +5, but that does not determine whether or not it's a 1 or a 0. The transitions do. Well, what do you mean by transitions? Well, with a logic 1, there's only one transition, whether it's going to the +5 or if it's going from the +5 to a 0. From 0 to +5 or from +5 to a 0. With a logic of 0, it does two transitions. One going from a 0 to a 1 and then from the 1 back down to 0, or from a 1 to a 0 and then from a 0 back up to 1. That's two transitions within a clock cycle. So those are your three self-clocking. You have RZ bipolar with 0 suppression, RZ polar, and you have CDI. CDI is different because of the word transitions. Let's take a look. Starting right to left, look at the clock cycle and look at the data. So the first one is a 0. So there should be two transitions. Now we always start with going to the positive side with our formats. It's just nature. And from what I understand, if you were to look at a oscope and how it starts, it should always start going to the positive and then back down to the negative when these things work up. It's just the way they programmed them. Why they didn't go negative, I don't know. I guess everybody wants to be positive now and then. Get it? Everybody wants to be positive. Man, really tough crowd. All right, so we have two transitions for a data of 0. The next one is a data of 1. Now, wherever that left off with the 0, that's where it's going to go in the opposite direction. In our case, it was at a 0, so we're going to go back up to a positive 1. We have another data of 1. It's going to go down. And then we get the data of 0s, so there are going to be two transitions. Now, there is a caveat to this. Anytime you see a 1, as long as it happens within the clock cycle, it doesn't worry about it. It's when the 0s come into play that it does the two transitions and they replicate the halfway through the clock cycle. So those are the two differences. The 1 doesn't care where it is. Most of the time it will start on the leading edge of the clock cycle if there is a transition. It has been known to drift off of that leading edge to somewhere within that clock cycle, but the distant end knows that. So when it sees a 0, everything resyncs back up because of the two transitions, and it is per the clock cycle. Holy crap, it's almost 11 o'clock. So here's what we're going to do. All right, we've pretty much got 2 hours in, and normally I'm past PCM, I don't know why I'm not faster, but oh well. Happens. We will see you guys at 1 o'clock, picking it up. We're going to go from the Nyquist theorem all the way through to 2 alpha. For the most part, 1 Charlie, 1 Delta is pretty quick, as well as 2 alpha. Getting you through PCM is about, I don't know, about a half an hour, and the rest of it should take close to an hour. So that is our game plan for this afternoon. Everybody go have a nice lunch, and we'll see you back here at 1 o'clock or 1300, whatever you want to use. Okay? We'll see you then.
Thank you, sir.
You're welcome.
Thank you,